In this video, I'm going to be working out a kinematics problem where a car is traveling at a constant velocity for the first portion of the trip and then begins to accelerate. And we're going to find a total delta x, and then we're also going to find the average velocity of the entire trip. And then we're going to finish off by drawing all the kinematic curves for the position versus time graph, velocity versus time graph, and the acceleration versus time graph. So the first thing you want to do is anytime you're looking for an average velocity, it sounds like it could be kind of complex if you have two types of motion in one problem. It's actually not very difficult if you find the total delta x first, so that's what we're going to do. Now for the first part of our motion, we're moving at a constant velocity, so we're going to use the formula delta x equals v times t because it's moving at a constant velocity. And if we plug in our two numbers, it ends up being fairly simple. Delta x equals 5 meters per second times 10 seconds. So we move a total of 50 meters for our first portion of the trip. Now for the second part of the problem, we can't use delta x equals v times t because it's not in constant motion. It is accelerating. And we have two variables here, and we will need a third. And since this problem is at 5 meters per second for the entire time, the beginning of the second part of the trip is starting off with the velocity of 5 meters per second. So we know our initial velocity is 5 meters per second. Now we're going to use the accelerated motion formula, delta x equals VIT, initial velocity times time, plus 1/2 AT squared, and then we're going to be able to solve for the delta x that way. So let's go ahead and plug in those numbers, and we get delta x equals 5 times 7 plus 1/2 a t squared. So if we find the product of these first couple, 5 times 7 is 35 meters plus 1/2 AT squared, which I'm going to plug into my calculator. We're going to get 61.25 meters. So if you sum those up, then we're going to have 96.25 meters as our total delta x for that portion. All right, now we're ready to find our total delta x. We're just going to sum up our two values, our 50 plus 96.25, and then that's going to leave us with 146.25 meters for our total delta x. Now, anytime you're looking for an average velocity and you have multiple types of motion, the best thing to do would be able to take the total displacement divided by the total time. So I'll put little subscripts for the t's. And then when we plug in those numbers, our total delta x we just wrote down is 146.25 meters. And the total time of our entire trip is 10 seconds plus the 7 seconds of the second portion, which equals 17. We divide those two, and that leaves us with an average velocity of 8.60 meters per second for our entire trip. Now, if we were to draw the graphs for this type of motion, it would look something like this. So we would have a position versus time graph, a velocity versus time graph, and an acceleration versus time graph. So if I were to sketch those, we would have a constant velocity portion that is moving forward. So it's going to have a constant positive slope. And then for the second portion, when it's accelerating, it's going to start off with the same slope because it starts off with 5 meters per second, but it's going to accelerate. So that slope is going to get progressively steeper for the second portion. And then if we wanted to mark the time, we could. We know this first portion goes up 10 seconds, and then this additional part goes up 7 more seconds, so 17 seconds total. Now for the velocity versus time graph, we are kind of changing modes. We're at constant velocity, so which means we have a constant positive line right at the 5. And then from there, it's going to accelerate, which means that it's going to slant upwards away from zero to show that the velocity is increasing at the same time intervals at 10 seconds and 17 seconds. You want to make sure you start above zero at 5 meters per second. And then for the second portion, it's going to be a constant positive slope to show that it's speeding up. Now, if you wanted to solve for the final velocity, you could. You would just plug it into an additional kinematic formula, and then you can go ahead and solve for that. So if you did something like a VF equals VI plus AT, you could go ahead and solve for that VF and then plug that in. Now for the final one, we have the acceleration. The acceleration for the first half is going to be zero because we do not have a velocity that is increasing, decreasing, or changing direction. It's maintaining a constant 5 meters per second. And then for the second portion of it, when it is accelerating, it is a constant positive acceleration of 2.5. So to keep a constant positive value, we're going to have a flat line that is above zero. So to sum things up, if you're solving for a problem that has a combination of some constant velocity and accelerated motion, make sure you only use this formula for the constant velocity, and then you can use different accelerated motion formulas for the second half. This one seemed to be pretty good, this one in red, to fit our needs of solving for delta x. When we wanted to find a total delta x, we just sum those two answers up together to get that grand total of 146.25. And anytime you want an average velocity for an entire trip, you can always use the total displacement divided by the total time. Make sure you sum everything up, divide them, and that left us with an average velocity of 8.60 meters per second. And then we went ahead and graphed each of those types of motion with the position, velocity, and acceleration time graph. So I hope that was helpful to you. Thank you for watching and listening.